Hi, good afternoon. Thanks for attending. So yes, I'm going to talk about essentially spoken language understanding, but done in an embedded way. And I'm currently part of the voice team at Sonos. But what I'm talking about is work that we've done with the team at Snips, and we've been essentially acquired by Sonos very recently. So in this talk, I will briefly introduce what spoken language understanding is, what are the challenges and benefits of doing embedded SLU. Then I will describe the pipeline that we use as Snips to do embedded SLU, and then I will give some metrics of performance in comparison with more common cloud-based approaches. So SLU is essentially the task of translating, extracting meaning from a spoken utterance, and we can divide it into two main building blocks. The first one is ASR, so automatic speech recognition, and the second one is NLU, which means natural language understanding. ASR translates a voice query, so acoustic features, essentially, into text. And then the NLU is responsible of extracting meaning from the text. So the context we are considering here is the one that is typical of closed domain voice assistants. For example, an assistant you could use to control the lights of your house. So a suitable way to express meaning is basically through two different concepts. One is the intent and the other is the slots. The intent expresses the intention that is underlying the query, the voice query of a user. So for example, turn on the lights. And the slots typically give all the supplementary information needed to complete the intention. In this case, for example, the room in which you want to turn the lights on. So embedded SLU. So the more commonly SLU is done on the cloud, which means that your voice goes through a device that sends your voice to the cloud, where your voice is processed. The device gets back a response from the cloud, and that gives feedback to the user. So this is very convenient because on the cloud you have basically all the computational power that you need to do the voice processing, which is a very complex problem. But on the other hand, on device, so in an embedded way, you have restrictions. So you have less computational power. You must have a low memory footprint, and at the same time you still have to run in real time. So in this talk, and the Snips in general, we took it as a reference hardware like a Raspberry Pi 3, which is kind of limited power. So you could say, why then bother doing SLU in an embedded way? Well, because it comes with some advantages. The first, most evident one is privacy. So your personal data, and especially your voice, which is biometric data, does not go to the cloud. You can reduce latency because you don't need a round trip to the cloud. Your assistant will have offline capabilities, so you don't need to be connected to the internet to work. And another important thing is that you can do a user personalization. So on the cloud setting, essentially user personalization is not possible because you would have to run like as many models as you have users on the cloud, which is costly, impossible. While if you do it in an embedded way, well, you can personalize the models for the user on his device. So at Snips, as I said, so we took as a reference hardware the Raspberry Pi, but the Snips platform is supported on a series of different boards. And we developed the inference library in the Rust language, which is convenient in this case because is very good at portability. It can be easily cross-compiled for different platforms. It's highly performing, and it's safe. So you can essentially, it's very difficult to put memory and safe code into production. So these are a series of advantages. So now let's go to the anatomy of this spoken language understanding system. So essentially, as I told you, you have the ASR part that does speech recognition, and you have the NLU part that does the understanding. But on its turn, the ASR can be broken down into two main blocks. One is the acoustic model, and the other one is the language model. The acoustic model is responsible to transform acoustic features into continuous streams of phonemes. Phonemes are essentially like the basic units in which you can divide human speech in one given language. And then this stream of phonemes is taken by the language model that transforms it into structured sentences, essentially, that then are fed to the NLU. So what is commonly done on the cloud is that ASR is general. So it means that it covers language in any given possible domain, which means that the models that are used for it are huge, both in terms of size on disk and also in terms of memory consumption. And the computation power you need to run them is huge, so they're not essentially suitable for embedded. So what I'm going to present here essentially is the approach we had at Snips and how we basically managed to fit what were the compromises and the hacks we need to make all of this fit on a small device. So the acoustic model is based on deep neural networks, as I said, which are typically very large models that are very computationally expensive and that need a lot of training data, so typically tens of thousands of hours of annotated speech and in-domain speech, which means speech that covers the scope of your assistant. So what we did at Snips is basically accept a trade-off between the accuracy of the acoustic model and its size. So we managed to reduce it to around 10 megabytes. And actually we needed much less data to train it. So as I will show in the following, this loss in accuracy can be compensated in some way. So the second part is the language model. Again, the language model is typically something huge because it has to cover the whole language, which means that the vocabulary is very large. It still needs to run in real time. It must be robust to different ways of expressing a concept, and ideally it would be suitable for customization. So at Snips, what we did is basically to specialize the language model, so what we call contextualization, which allows us to reduce the size of the model. But then we had to come up with a strategy to handle out-of-vocabulary words, and it allows on-device personalization, which means private personalization. So how did we do it? Essentially, contextualization is very simple. Instead of having a huge language model that covers all the use cases possible, we just had a language model that is specialized to the domain of the given assistant. For example, if it's an assistant for lights, then it will cover a very small vocabulary that is necessary to command lights in your apartment. This comes with a problem because if the user speaks about something else or uses a different formulation that wasn't used during training, then you're going to get some out-of-vocabulary words that are not handled by the assistant. So what happened is that we had to come up with a strategy that considered confidence on single words to exclude the words that had too low confidence as consider them as out of vocabulary. and it turned out to work quite well. And the third thing is on-device personalization. So we were able to adapt the language model by dynamically changing it on the device to adapt to the user. For example, if you want to add a new contact on your phone book. And then the other part is the NLU, as I told you. Again, here are some challenges. So we needed it to be fast at training. We needed to be trainable with a small amount of sparse data, and we needed to be robust to different formulations. And so essentially what we did is kind of the same thing. So we use lightweight models. So we use the logistic regression for intent classification, and conditional random fields for slot filling. And essentially, we did also contextualization in a coherent way with the language model. So we basically we trained the language model and the NLU on the same data, which enforces coherence between the two. And our NLU library is open source, and it's available on GitHub. Then let's go to a few benchmarks. So we've chosen a couple of use cases to benchmark our solution that lie at the two extremes of the spectrum we want to cover with the Snips solution. So the first one is smart lights. So it's an assistant that commands the lights in your apartment, and it belongs to the category of the small vocabulary assistant. So it has around 400 unique pronunciations for words. And then on the other side of the spectrum, we chose the music assistant, which typically has to handle large catalogs of artists, albums, and tracks. And here we have a very large vocabulary of around 180,000 pronunciations. So we benchmarked the Snips solution, which runs on device in real time, so on a Raspberry Pi 3, against the Google Cloud solution. And the metric we used is essentially the percentage of perfectly parsed queries, which means the queries for which you accurately recovered both the intention and the corresponding slots. So typically, if you want to play an artist, then you should detect that the intention is to play, and the slot, and you should recognize what artist you're gonna need to play. So these are the results of the benchmarks. So I have to point out these are benchmarks in a closed field, which means that essentially the speaker is close to the microphone, as opposed to other possible benchmarks that we can do, which can be in far-field situations, so a speaker is far from the microphone, or in noisy situations in which there is like a large background noise. So in this case, it's clean, closed field, let's say the easiest situation possible, and as we see, the Snips solution performs on par or better with respect to the Google one. And let's say the most interesting result is probably on the music assistant part. So in red, you have the accuracy of human transcribers. So in theory, it's difficult to do better than that. But what happens is that Snips, so we chose 3 tiers of artists. So the 1K most popular, then the artists between 4.5 and 5.5K of popularity, and then between 9K and 10K. And here what we found that through our training, we managed to get essentially the same accuracy across all the tiers, or something close that was not degrading too much, while both for human transcribers and for Google, the accuracy is decaying very fast with with the ranking of popularity of the artists. So yes, maybe the conclusion of this talk can be that yes, we were able to do essentially spoken language understanding on a small device with a lot less computational power with respect to the cloud, but without essentially degrading the performance. And I guess that's it. Thank you.
We have time for questions before the break. Abdel?
Hey, thanks for the presentation, very interesting. So about the last benchmark, you didn't say anything about the data sets.
Yeah, the data sets we benchmarked on. Yeah.
No, you train on.
The train on.
Yeah, the training data set, because.
Yeah, okay. Essentially, those are data sets that can be made through the Snips console. So you can enter the utterances you want you want to support that are divided between different intents, and you can define also the content of the slots you want to support. And then what we do at Snips, we train on this data that you can construct on the console, and the data is also available. And it's open source.
Okay, that's great, thanks.
Yeah, you have a mic just there, yeah.
I have a question, because now Chinese apparently are very good in voice recognition, the companies like iFlytek and so on. Do you have any comment on this? Apparently they translate everything in every direction and so on.
About voice recognition in Chinese?
Companies like iFlytek, for example.
I don't know this company, but do they do it on in an embedded way, or they do it on the cloud?
Oh, I don't know exactly.
Yeah, because of course, I mean, there's a lot of work on speech recognition in Chinese. But for example, at Snips we supported like 7 languages. But we didn't get to Chinese yet. It was on the roadmap, but.
But you make also online translation?
No.
Okay.
No translation at all. This is just for understanding. So essentially, you get a voice query, and you extract what was the meaning of the voice query. And again, it's not general purpose. It's intended to be able to be specialized to a certain scope, which could be, I mean, larger or narrower, but again, it's closed domain. It's what you call it's not a general assistant, it's not a chatbot, it's not...
Like predefined commands, something?
It's not predefined commands,
like
it's a predefined domain.
Okay. Mm-hmm.
Yeah. But it's natural language.
What kind of audio pre-processing you do before you do this recognition?
Pre-process?
Yeah.
It's just extraction of MCC features from audio. It's audio processing essentially. Then it goes through the acoustic model, which is a neural network, and then you just get probabilities, so it's finished. But pre-processing, and then there can be some pre-processing of the sound. So there can be auto-echo cancellation and all of that. But I mean, here I didn't talk at all about that.
Could you show again the GitHub address?
Yeah. It's Snips NLU.
Okay, thanks again, Francesco.